Hey everybody, this is Mr. Conklin, recording from my world famous studio at home. Put that in scare quotes, world famous, quote unquote. Happy Thanksgiving, by the way. It's Thanksgiving afternoon for me over here in Ionia. I wanted to finish up the prep videos about this entire chapter 3. We've been talking about factoring and solving large polynomials and all the tricks we use to do that. Couple things to cover. With the first video had a normal polynomial that you could factor normally, but eventually we're going to hit a polynomial that we simply cannot factor by our normal methods. If you remember, the normal methods are GCF, unfoil, binomial squared, difference of two squares, grouping, magic pair, and then the optional method called substitution. And none of these work here. It doesn't have a GCF because 55 and 6 don't have anything to do with each other. It has 5 terms, so you can't factor by grouping. And all the other methods require a degree of 2 or at least 3 terms, or 2 terms, like with difference of two squares. No matter what happens, this thing flops. So what do? Well, ultimately, we're going to start guessing and checking. But just as a quick review, the first thing I'd like to cover is something called the fundamental, sorry, I'm writing so slowly, fundamental theorem of algebra. And sorry for my sloppy handwriting here. If you could see me, I'm sort of bending over one arm of my armchair in order to reach over this sort of wobbly TV tray to get underneath the document camera here. So sorry, please cut me some slack on it. I normally try to have a little bit better penmanship than that, but whatever. The fundamental theorem of algebra basically says that in any polynomial, and I'll explain more about that in a second, in any polynomial, basically the things we've been dealing with this chapter, the degree equals the number of roots. And just so you're aware, the word root is a synonym for solution, which is a solution for x-intercept. If it's real. If it's not real, then there's no such thing as an x-intercept, as an imaginary spot. And there's also a fancy term called zero of the function. Sometimes they just call it zero. So the book likes to call it zero a lot. But when they say find all the zeros, they're talking about find all the x-intercepts, or find all the solutions, or find all the roots. Does that make sense? All of these mean the exact same thing. The only catch is we only use the phrase x-intercept if they're real. If they're non-real, then it doesn't make much sense talking about an x-intercept. But definitely root, solution, and zero of the function are identical. And x-intercept means the same thing if they happen to be real. Okay? So the first fundamental, or the regular fundamental theorem of algebra says that if you have a polynomial, just so you're aware, polynomial is a sum of one or more terms. One or more terms. The exponents are all whole numbers. Now be careful there. Whoops. W-H-O-L-E, I can spell. Whole numbers doesn't necessarily mean round numbers. It does not include negatives. It does not include, well, it also obviously doesn't include decimals and things. So this would include 0, 1, 2, 3, and up. So the exponents all have to be whole numbers, and the bases are all the same. So if you're using x as the variable for the base, you got to use it all the way through. Like if I had x to the 4th plus something y to the 3rd, I wouldn't count that as a regular polynomial. So we wouldn't be able to play with it. Okay. So bases are all the same. Okay, so the very first thing is the fundamental theorem of algebra. Why is this useful to us? It tells us how many roots to look for. In this case, the degree is the highest power. I remember that from previous years. The highest power in the whole polynomial. In this case, that's 4. So we're expecting 4 solutions on this thing if we set it equal to 0. Does that make sense so far? Let me see if I can get this thing to focus. Hang on a second. Yeah, that's a little bit better. So it's not going to help us find the actual numbers, but it'll help us know when to stop. Number 2, the interval containing the roots. In case you're wondering why I use root instead of solution or 0 of the function, it's short. Roots is easier to say, and it's what have you. You could call them zeros, but people are sort of saying, well, what does that mean? Does that mean x equals 0 all the time? It gets a little confused. It doesn't. It just means x equals 5 if it's a solution. They call that a 0 of the function, or just a 0 for short, and sometimes people get confused. Anyway, the interval containing roots is x belongs to square brackets, negative last coefficient. I'm going to abbreviate that. I hope that's okay. And then positive last coefficient. So anywhere in this particular case, you notice the last coefficient is 6. So the one that goes after, there's x squared, regular x, and then there's a constant term, which is the last coefficient. In this case, it's 6. So we would say that x is somewhere between -6 and 6, including those. Okay, so you would not look for any roots beyond that. You would not guess x equals 7 or 10 or 12 or -8 or -12. It's got to be in between -6 and 6. Okay, the third is the rational root theorem. The rational, if you remember, and THM is abbreviation for theorem. Rational means fraction. Rational numbers are numbers that can be written as a fraction with a round number on top, round number on the bottom, like 2/3 or -5/6. The rational root theorem basically says all possible rational roots, I'm going to abbreviate here, it looks like rattle, all possible rational roots can be found by this sort of master fraction, plus or minus factors of the last coefficient over plus or minus, I'm going to do ditto marks here, factors of the first coefficient. Does that make sense? This just means the same as above. That means it's called a ditto mark, in case you haven't heard that before. It means ditto, ditto. It's the same as above. So plus or minus factors of the last coefficient over plus or minus factors of the first coefficient. In this particular case, it would be plus or minus, I'm going to list all the factors of the last coefficient, which is 6. So 1 and 6, you don't have to list them in order. I actually don't. I list them in pairs. And then 2 and 3. Those are all the factors of 6. And then at the bottom, I only need all the factors of 55. There aren't actually all that many. 1 and 55, and then 5 and 11. Okay, so that's the compressed list, we sometimes call it, of all the possible rational roots. What that really means is that you could have 1 over 1, -1 over 1, 1 over 55, -1 over 55, etc. You can have a lot of them. You notice there are 4 numbers here, and there are 4 numbers here. Whoops. Well, the total number of possible fractions is going to be this times this. It's going to be 4 times 4, which is 16, but then times 2, because it's going to be twice as many because you're including the negatives as well. So the 32 possible fractions. Okay. Excuse me. The reason we care about the list of fractions is because those are all the nice roots that are possible. I mean, obviously we can't use all of them because there are 4 roots maximum. If you remember the degree up here, it's 4. So if all of them are rational, then it'll be 4 of these fractions in here somewhere. Again, no guarantee that the roots are all rational. No guarantee that any of them are rational. They could be irrational, like square root of 3. They could be worse. They could be non-real, like 2 plus 3i. We don't know. But if they are nice roots, they'll be in this list. When we're guessing and checking, this is the list we're stick to. You do not have to guess and check anything weirder than this. Now, it's a long list. 32. There are a couple of duplicates. Actually, no, there aren't. Wow. I think you might have just 32 pure fractions in here. But anyway, you would not have to guess beyond that list. You wouldn't have to start guessing. Like, in other words, I would not guess 5 over 3 because that's not on the list. Even 2 over 3, not on the list because there's no 3 in the bottom. Does that make sense? Anyway, so far, summary, we know there are 4 roots in this thing. I have no idea where they are except they're between -6 and 6. So I don't go beyond that. And the rational root theorem will give me a possible list of the numbers, hopefully between -6 and 6, where they could be. And I'm not going to guess anything outside of that list. So it is kind of a limited list, which is good. You don't want to be guessing forever. And when we're guessing and checking, we want to do it logically and not guess all over the place and guess forever. Pardon me, I'm just moving some stuff out of the way. Next, something called Descartes. This is a little more recent. Descartes. Sometimes they spell his name with a capital C here. Descartes' rule of signs. Descartes' rule of signs basically says the number of positive roots is equal to the number of sign switches. I'll tell you what that means in a second, although we went over it in class, from term to term. Term to term. And I'm going to say something kind of mysterious here. Possibly minus an even number. I'll put a little star there because there's going to be an explanation for that coming up soon. The number of negative roots, I should say the sign switches from the original polynomial, like up here, f of x. Let me cram that in here, of f of x, just so you know what we're talking about. The number of sign switches of f of x going from term to term to term. Basically, if you're looking here, if you're switching from positive to negative or negative to positive, that would be called a sign switch. So let's go back over here. The number of negative roots is the number of sign switches. Of, this is a little bit more mysterious, f of negative x from term to term. To term. But I'm going to say that same mysterious thing, possibly minus an even number. Okay. Now, there's a quick way to get f of negative x. Switch the signs of the odd powered terms. I'll give you an example of this when we actually run this problem. Odd powered terms of f of x. So in other words, go to the original polynomial, and then anytime it has an odd powered term, switch its sign from positive to negative or from negative to positive, whichever you need. Okay. So in this particular case, let me just give you a demo. Up here, f of negative x. What you could do if you want to do it the long way is just plug a negative x in for every single value of x and then simplify it. But what will actually happen is that you'll have the same on any even-powered exponent, but then it'll switch the sign on any odd-powered, minus 247x cubed. This is an even-powered one, so you keep it positive. 275x squared. Sorry, this thing is wobbling around. This is an odd-powered. It's power of 1, so it's going to be minus 89x. And then this is an even-powered. It's x to the 0. So they consider that an even-powered exponent. So don't switch that sign. So this is f of negative x. So if you want a quick way to get f of negative x to check your negative number of signs switches, just change the odd-powered terms from positive to negative or negative to positive. Does that make sense? Okay, we'll get back to that in a bit. But way down here, Descartes discovered that the number of sign switches in the original thing gives you the number of positive roots. But it could be less than that by an even number. How come? Because of what's coming next. 5 is called the conjugate root theorem. A conjugate, I'll show you what that is in a second. We've gone over it. Theorem. In any polynomial, and polynomials are what we're talking about in this chapter. In any polynomial, if a non-rational number is a root, then its conjugate, I write so slowly, sorry, conjugate must also be a root. What do I mean by non-rational? Basically anything with a root with a radical. Anytime you have a root with a radical, which is how you can get a conjugate in the first place, then its conjugate must also be a root. For example, if, sorry, I need x equals, if x equals 2 plus radical 3 is a root of f of x. By the way, it's not a root of the f of x we're using above. This is just an example. Then x equals 2 minus radical 3 is also a root. Guaranteed of f of x. Does that make sense? So it's kind of a 2-for-1 plan. If you get a root that has a radical in it, then I guarantee you have 2 roots for the price of 1. You're going to have its conjugate as a root as well. So 2 things that are interesting about that. Number 1, if you have a radical root, you get another one for free. So you cut your work in half, at least in that little part. But there's something, there's a fancy word, corollary. That just basically means something that follows. So corollary is sort of like, oh, this is true, and by the way, that makes this little thing true. This little thing is actually going to come in really handy. So non-real, by the way, you could also, you notice this is 2 plus radical 3. It also works with non-real numbers. So if x equals 2 plus 3i is a root, then x equals 2 minus 3i is a root. Does that make sense? So it works with, remember, I is a radical. It's radical -1. You don't have to write it as that, but remember in the back of your mind that I is a radical. Yo, man, I is a radical. Yeah, I know. It sounds like bad English. It isn't. So if x equals 2 plus 3i, x equals 2 minus 3i has to come with it. Okay. So the corollary, non-real roots, like the ones with i's in them, Non-real roots always come in pairs. Now, we sort of said that up here, that any radical roots come in pairs. Like if anything with a radical, if it's a root, then it comes in pairs. It's not going to come alone. But the reason we're so fascinated about non-real, which is basically with anything with an I in it, those are non-real, which means they're not positive and they're not negative, which means we won't be able to detect them in this original thing up here. Now, if you're trying to say, hey, I've got, let's just say we have 3 sign switches or somewhere, you can say, oh, there are 3 positive roots. Maybe. But if 2 of them are fake, then you'd only have 1 positive. Could you ever have 1 fake, like imaginary root? No. They always come in pairs. So let's say you have 10 positive roots. Maybe. There might be 10, but there might be 8, or there might be 6. Or there might be 4, or there might be 2, or there might be 0, because some of them might be fake, and the fake roots always come in pairs. So you could start with your biggest number, but then subtract 2, subtract 2, subtract 2, until you run out. That's why it says possibly minus an even number up here. That's because that's when, if there are imaginary roots in there, they'll drop out in pairs. They'll never drop out alone. Okay? That is largely what we covered in the second portion of the chapter. So let's actually do this. Let me rewrite this. It's going to be, see if I can actually get this on screen too. F of x equals 55 x to the 4th plus 247 x cubed plus 275 x squared plus 89 x plus 6. So this is regular f of x. So the very first thing I'm going to ask on a test is, what's the number of roots? The answer to that is 4, because that's the degree. Fundamental theorem of algebra says that. And then what about the interval? Where are the roots? You would say that x belongs to the closed interval, that means including the ends, from -6 to 6. So we know the roots are in between -6 and 6, guaranteed, because of the last coefficient here. What is the list of possible rational roots? I think we already did that. I'll just recopy it down here. It's plus or minus 1, 6, 2, 3. Yeah, I did do that up above. It's up here, but I'll copy it down here just so we can have a reference to it. And then 1 and 55 and 5 and 11. Okay, so those are the possible rational roots, like 1 over 1, 1 over 55, 1 over 5, 1 over 11, 6 over 1, 6 over 55, 6 over 5, 6 over 11, and so on. So you have a lot of possible fractions. Those are the ones we're going to be using to guess. Let me see. Descartes' tool of signs. How many positive roots? Well, let's go look at the sign switches on this thing. Well, this is positive, 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 positive. That's interesting. Guess what? The number of roots, there are no sign switches. This is claiming there are no positive roots at all. And we can't subtract an even number, so that looks like that's absolutely concretely true. There are no positive roots in here. Number of negative roots? Oh, let's find out. Now you have to go up to f of negative x. I already did that up here. So let's check the number of sign switches. This is positive and this is negative. That's one sign switch. I sometimes do these arcing arrows to show a sign switch. Negative to positive, that's another sign switch. Positive to negative, another sign switch. Negative to positive, another sign switch. See what I mean by sign switch? So plus, minus is one switch, another switch, another switch, another switch. So there are 4 sign switches for the negative test. So there are theoretically 4 negative roots, but or 2 or 0, because some of these might be fake, they might be imaginary. which are neither positive nor negative. If they're imaginary, they always go missing in pairs, which means it could be 4 real negative roots, or there could be 2 real negative roots, or there could be no negative real roots at all. They might all be fake. But there's no such thing as having a single imaginary root. So they always go missing in pairs. Does that make sense? You might be wondering, like, well, if it's degree 4, there are 4 total roots. Didn't we know that ahead of time? If there are no positive roots, doesn't that mean all of them are negative? No, it doesn't, actually. Sometimes I've run a problem like this, and it comes up 0 here and 0 here immediately. No sign switches. We don't do the blah or blah or blah. It's just 0 from the get-go. I mean, it's kind of rare, but I can actually show you one a little later. And that would mean that there are no real roots at all. They're all imaginary, which would actually be good news for us, because in the guess and check, the only ones who are responsible for guessing and checking are nice numbers, fractions. You are not responsible for guessing radical roots or imaginary roots. So if you got 0 here and 0 here, you would, unless it factors and you're super lucky, you would say cannot find solutions or something like that, and then move on to the next problem. Don't expect that on the test, by the way. I will put some actual real roots in there. So, but I'll give an example a little later on, maybe in the next video. But for right now, let's run this thing. We've got quite a few things to narrow this down. 4 roots, none of them are positive. And it says the interval is from -6 to 6. We can do better than that now. Remember they said there were no positives? I can tell you that they're from 0 to 6. Because there are from -6 to 0. Because none of them are positive. You're not going to have to test any roots that are positive. So from -6 to 0. So over in here, half of these roots we can throw away. All the positives. So +1, +1/55, +1/5, throw away. So we are getting ready to guess. We have to guess negatives. And if you remember, we guessed these by using synthetic division. That's the fastest and most efficient way to test. And by the way, synthetic division does 2 things. It tests to see if, hopefully on the bottom row, we get an answer of 0 at the end. That means it's a root. And if it does work, you'll have already ripped the root out, and there'll be a new polynomial in the bottom row. Let me show you what I'm talking about. Let's just be easy and try -1 as the first guessed root. So this is called the box number. I'm going to fill in the coefficients for synthetic division: 55, 247, 275, 89, and 6. I will tell you there is no honor lost in having a calculator in this portion, and I will be allowing a calculator on this particular test. Partially because when you think that 247, multiplying by 1 is not that bad, but let's just say we were trying -6, 247 times 6, and then add that to 275, yikes. We can do it. It's not like pre-calc students can't do that off to the side on paper, but it takes a long time, and time is of the essence on the test, so go ahead and punch it into a calculator if you need to. So I'm just going to add 55, multiply -55. Here we go with the mental math. This is going to be 2, 192. This is going to be -192, 275. The way I do these in my head, by the way, I subtract 100, then subtract 90, then subtract 2. And there are a couple other tricks you can use. But actually, I'm just going to do it the old-fashioned way. 5 minus 2 is 3. Borrow. 17 minus 9 is 8, and then 1 minus 1 is nothing. So it's +83, so this will be -83. This will give you +6, multiply -6, and glory be to God, we've got a root. You're welcome, by the way. I did design that so that it wouldn't take forever. Now, if you notice, this used to be 55x to the 4th. When you synthetically divide, you're ripping a root out. So there's one less root in here. This is 55x to the 3rd plus 192x squared plus 83x plus 66. I would strongly advise you take a good hard look at this and see if it factors by grouping. In this case, it doesn't. The pairs have to be proportional. This one, you're multiplying by something to make it bigger. This one's getting smaller, so there's no way it's proportional. Anyway, so we have to keep guessing. We've got 1, which is great. Now, keep in mind, see this last number? The roots are still from -6 to 6, or in our case, from -6 to 0, because we know positives aren't going to work. So we can try the next one. I'm going to try -2. If it doesn't work, it doesn't work. You know, it's no crisis or anything. It's just more paper. Let's try it out. And hopefully I'll be able to tell you, like sometimes you'll be able to tell when this is just not working. So you should be able to abandon ship without doing the whole thing. This is -110. This is 82. This is -164. This is not looking good, by the way. This is -79. +158. 164. Yeah, that's not good. So skip number 2, -2. I'm going to try -3. Reset this. It's going to be 55, 192, 83, 6. Let's try that. So this is 55. This is -165. 75, 85. I use 27, I think. This is -81. This is 2, -6, and you're welcome. So this is another root. X equals -3. Again, no guarantee it's going to be a round number like that, but it's going to be more likely than not if I design the test. So we'll see. There may be a few fractions in there, so beware. This, we just ripped another root out successfully. This is 55x squared plus 27x plus 2. Now, does this thing factor? Well, interesting question. The answer is, I don't know. Let's find out. Hang on a second. I want to make sure I copied the original. I have the answer worked out, by the way. Yes, it does factor. Here's what I would do. I am going to use, you could use quadratic formula on this, by the way. It would be really, really big numbers. But just because I haven't done it in a while, I'm going to do magic pair. By the way, no guarantee magic pair is going to work. It might not factor. So have quadratic formula memorized in the back, just in case. So let's see what happens. I need a pair of numbers that multiply to be these and add up to 27. So I'm going to do 1x times 110x. That's way off. 2x times 55x. It's better, but it adds up to 57. I want 27. 3 doesn't work. 4 doesn't work. 5 should. 5x times 22x. Ding, 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 ding. That is our magic pair. Let's try this out. So I'm going to scoot it in over here. Sorry, I'm really crammed up against this dinner table here. It's a TV tray that I'm balancing on. That's why it's wobbling so much. So it's going to be 55x squared plus 5x plus 22x plus 2. Now I'm going to factor by grouping. So it's going to be 5x coming out of this one with an 11x plus 1. Don't make it a 0. Plus there's a 2 here, and then 11x plus 1. And this works. So I'm going to pull this out. So 11x plus 1, and then 5x plus 2. That's the factored version of what's left. There are 2 roots here, and if you want to solve them, set them equal to 0. I'll do it over here. So 11x plus 1 equals 0, and 5x plus 2 equals 0. Sorry, it's kind of crowded. So subtract 1 from both sides. Hope you can still see that. 11x equals -1. And if you divide by 11 on both sides, you can have x equals -1 over 11. That's one of our hidden roots. Here, subtract 2. You get 5x equals -2. Divide by 5. And our other mystery root is x equals -2/5. So if you notice, I've got root number 1, 2, 3, 4. That's all 4 of them. We're done. Whoops, we're pointing the wrong one. And we're done. And if you notice, negative, 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 negative. All four of them are negative, exactly as Descartes predicted. No positives, and it was 4 negative roots. They could have been fake, but in this, it turns out we were lucky and they weren't. Does that kind of make sense? So there is an example of how to use one of these things where no imaginary numbers show up, but still finding all the parts. Again, can you find the number of roots, which is just a degree? Can you find the interval containing the roots, which is just the plus or minus version of the last coefficient? Can you use Descartes' rule of signs to find the possible positive number of positive roots and negative roots? That's the sign switches from f of x for positive roots and for f of negative x for negative roots, possibly minus an even number. So if you come up with an answer, again, of 5, you have to write 5 or 3 or 1. Does that make sense? Because they could have a bunch of imaginary numbers missing in pairs, and they always miss in pairs. And that is that. So I'm going to call this video quits, and in the third video, I will show people how to handle a situation where you have imaginary roots and how to find them. Anyway, so take care, God bless, have a happy Thanksgiving, and talk to you later. Bye-bye.